All right, starting from the top, we're talking about a reciprocal function. By reciprocal, remember that we are dealing with essentially anything that is written. The reciprocal is 1 over x, or if I have a over b, the reciprocal is b over a. Essentially, I'm swapping the numerator and denominator. Has nothing to do with swapping x and y. It has everything to do with swapping two different parts of a fraction. And how does that change things? And what's the relationship with the original? Well, that's what I'm going to investigate. Okay, sketch the graphs of f of x and 1 over x on the same Cartesian plane. If you have a ruler, great. If you don't, try to do your best. What I'm doing right now is drawing. This is f of x. Okay, so that's, f of x equals x, or y is equal to x. The slope is 1. The y-intercept is 0. You know what it is, mx plus b. Now, for a reciprocal function, before any of the transformations, you learned this in grade 11, it's supposed to look like this, where you, remember, you have a asymptote. That is my vertical asymptote at x equals 0. And a simple parent reciprocal function also has an asymptote on the x-axis, which is labeled as y equals 0. This is a vertical asymptote, VA. That is a horizontal asymptote, HA. And what is it supposed to look like? Just to remind you of what you did last year, let me do a quick table of values. Right, f of x is equal to 1 over x. And I need to use 6 points. If your teacher was trying to be thorough, they would have at least done 6 points. They did, what is it? Probably -2, -1, -0.5. And then sure, I could do a 0. And then 0.5, 1, and 2. The reason I chose 0.5 is because the y value looks pretty nice. Now, let's start with the positive. 1 divided by x, 1 over 2, that's 0.5. 1 over 1, that's a 1. And 1 over 0.5, you can use a calculator, that's 2. Let's jump over 0. If it's 1 over -0.5, that's a -2. 1 over -1, and 1 over -2, that's a -0.5. So you should see a bit of a mirror image between these two. It's just that it's positive and negative. What happens when x equals 0? Well, you can't have 1 divided by 0, right? That does not exist. You can't. We have a vertical asymptote at that location. Plotting, it becomes 1, 1, 0.52, and 2, 0.5. The reason I chose these 3 dots is because it does demonstrate a nice curve, and we're going to connect that. -1, -1, -2, -0.5, and -0.5 is -2. On the opposite side, there is also a nice curved triplet of pairs. And if I were to connect it and I continue this pattern as I get closer and closer to the asymptote, I don't touch it, but I get really close. It looks something like this. Does that look familiar? Is that little dance your teacher might have done? No? Sort of, maybe? Okay. With these 2 graphs, so my blue is g of x, which is 1 over x. Let's discuss some of its characteristics. And it might seem redundant to you right now, but it's going to help with tomorrow when we look at an unfamiliar scenario. Okay? Zeros. Let's do the easy one. For the straight line, y equals mx plus b, what are the x-intercepts? There's only one. That's right. When x equals 0, my y is a 0. Domain. Does it look like it's ending anywhere soon? No. X belongs to... You can do x belongs to any real number. If you want to do it as an interval, you could say it goes from negative infinity to positive infinity. Both are okay. I'm going to zoom in because you should have the graph in front of you. Range. Does it stop anywhere up or down? No. So y belongs to any real number. And if you want to write it as an interval, you can as well. What is the interval when the function is positive? So when it's above the x-axis. For the red line, it's right here. So it is positive when x is greater than 0. So an interval would be 0 to infinity. What is the interval when the function is negative? That's all down here. So the function is negative when it is to the left of 0. What is the interval? So this is something new. I'm going to highlight it. The function is increasing or decreasing. Don't overcomplicate it. I'm simply asking you, is the y value getting bigger or is it getting smaller? So take a look at this curve or this red line. Then what x values is this line getting bigger? Or when is the y value increasing? Right. It's never decreasing, right? So interval when the function is increasing from negative infinity to infinity. And when is the function decreasing? Never. Okay. Yes?
Could you explain the increasing and decreasing?
Sure. Increasing and decreasing simply means, is the y value getting bigger or smaller? So typically what I say is, from left to right, you take a look at it. Are you, and you're walking this way. You're going left to right. Am I going uphill or downhill? Uphill. So it's increasing. I'm going up the y value, right?
It's always from left to right.
Exactly. We're always going from lowest x to largest x. Where am I increasing? The entire graph. Where am I decreasing? It's never going down, right? I'm never going back down. But the conversation changes a little bit when we talk about the reciprocal. So consider this. Here's a relationship between a regular graph and its reciprocal. The zeros. For the original, x equals 0 was my x-intercept. Do I have a 0 for this curve? No. Instead, x equals 0 is a vertical asymptote. So I'm going to add a little note here saying x equals 0 is actually, it's an x-intercept. But for the reciprocal, that same point turns into a VA. Domain. Because I have a VA, the domain is, once again, XER, but because I have a vertical asymptote, I have no choice but to consider that as in my domain. Yes?
Do you only write the vertical asymptote?
For now. You'll see me work on the horizontal asymptote right now. Okay, you ready? For the range, I want to say any y value goes, because it goes up forever and it goes down forever. But there is one point that y cannot reach. and that's 0. Anyone want to look at this and maybe use your grade 11 skills to tell me why is the y value never a 0? Got 2 people. Anyone else want to dig deep? Charlie?
Because it's never going to touch the asymptote.
True, but can you explain that based on this function, based on that? Why can't the y value, so why can't I ever have this? Is what I'm asking. I'm not trying to, it's not a trick question. It's right in front of you. You just have to know where to look. Cecilia?
Because it's equal to 0, that's
This side, I'm going to challenge you to look elsewhere because the x value, we've already established x can't equal 0. So we don't have to worry about that. Something, yeah, we'll go back, yeah?
because it's always getting divided by it. So it's just like splitting it.
Yes.
A bunch of times.
And, okay, so you're always dividing. What's being divided? 1.
So it's always just going to be a fraction.
It's always going to be some decimal. It's going to be 0 point something, but it's never going to equal a 0, no matter what. Okay, so if the denominator has something there, that's not an x, right? It always has some constant, then this y value can't be a 0. So let's leave it there. Now, interval where the function is positive. Well, for the asymptote, all of this right here is on the positive side. And so, interval where the function is positive does not change, does it? It's identical. Okay. Next, where the function is negative, same thing. Just like that red line, this part of my reciprocal is negative. So it's exactly the same as my original. Here's the funky part. Here's the funky part. Look at the graph. When is this graph going uphill? Am I ever going uphill? No. Then that means every single part of that curve I am going, I'm always going. Yes, fair, I am teleporting from here to here, I get it, right? I'm disappearing here and suddenly appearing here because I can't touch that line. But putting that concept aside, every single x value that I travel, I'm going downhill. So what does that look like here? Am I increasing? No, never. And am I increasing? Everywhere else, right? But of course, x can't equal 0, right? But remember, x can't equal 0. So what is the relationship? When we talk about the reciprocal, the one thing that does seem to sort of get wonky that you have to pay attention to is that what used to be increasing is now decreasing. What used to be decreasing becomes increasing. That's it. That's the main difference. So as a summary, consider some relationships that we find. Consider this. So whatever y values I have, the reciprocal will always have the reciprocal y value. So if I have f of -1 is equal to 2, then g of -1 will be the reciprocal. It sort of makes sense. All have the same positive or negative intervals, but they will have reverse increasing or decreasing intervals. We always see it to be true, always, interestingly enough. Well, it's not so interesting if you try the math and you plug in numbers. Whenever f of x equals 0, g of x will have a vertical asymptote, which makes sense because you made the denominator equal to 0. A reciprocal function can never equal a 0 because Charlotte just told us that the y value, in this case, the fraction has a 1 on the numerator. It'll never equal a 0. The local maximums of f will be local minimums of g. That's something we can sort of discover together as we do more questions. If it was up here, it suddenly becomes down there because we're doing reciprocal. Now, oh, Will, yes.
I was just wondering, is it true that it'll touch the asymptote?
It doesn't touch.
Even though it's like 1 over infinity, it's small.
Because if you want to be technical, it's not quite 0, is it? Right? Even 1 over infinity, as large as it is, in the Earth, we don't care about it being that small. We just say, oh, it's a 0. But mathematically speaking, it's still technically a number, as infinitely small as it is. I know it's wonky. It depends on what field it is. Because I could prove to you that 0.99999 is also equal to a 1 mathematically.
Yeah.
But in this world, when we talk about functions, that's not what we want to dive into. It's a little wonky. So just bear with me. If you're interested, I'd love to share that proof with you, but we'll get to that after.
It's not quite infinity, is it? It's like, because infinity is not like a constant, right? It's like.
I know what you're saying.
Okay, I don't know how to say it, but it's that, like, you're increasing, like you're increasing like positively in almost like in a direction.
I know what you're saying.
Yeah, it's not.
To quote my beloved Slavic teacher when I was in grade 12, you become infinitesimally close to the line.
Right.
Get it now? So it's not infinitely large, but infinitely close to the line. Does that make more sense? So still the concept is infinity, but in a different, right? Okay. Do you know I still keep in touch with him? His name is Mr. Mendelovitz, and he sometimes supplies at Northern. You might have seen him. He's a big, jolly guy, plays tennis. His wife got sick, so he had to retire early. But I see him once in a while. It's really cool. I was such an annoying student. It's a fun student. Me and my really good friend at the time, we sat where Shay and Ethan was, right in front of him. And for whatever reason, while he was teaching, I don't know what got into us, we started beatboxing Billie Jean and Michael Jackson. And so we would look at each other, be like, and then he started doing the bass line, and then we started doing something. He got so angry, he threw the textbook on my friend's desk. And he's like, would you stop it? And then we just froze. We were thinking like, oh, this teacher's so mean. We're like, oh man, we really pushed his buttons. We're so stupid. But it's a very endearing story. I still remember it. Yeah. Anyways, I still got my mark, so he didn't hate me. He just got annoyed by me. Let's move on. Well, that was all recorded, I realized. That's pretty bad. Okay. Let's do this. A taste of calculus, everyone. You are going to learn in calculus. This is an acronym that I got from a textbook I used when I was in high school. They don't use it anymore, but I think it's very useful because it gets you to remember every little part. And that is this AIC. This AIC. Now, in calculus, you will have to learn all these other things, M, I, and C, because you need to. But for now, I think it's a good opportunity for us to get used to the first 5, so that when you do get into calculus, it's just like, oh yeah, an extra 3 steps, no problem. This A, without the M, okay? This A. We are going to take a look at this relatively easy reciprocal function. We will talk about the domain based on what we've learned. Talk about the x-intercepts and y-intercepts by calculating them. Talk about the symmetry, we'll skip for now. Talk about the asymptotes that's available, and then talk about the intervals of plus minus to confirm we're drawing it right. What are we doing here? We are doing the opposite of what we did in chapter 2. In chapter 2, I gave you the equation, or I gave you the x-intercepts, and you used it to draw. Here, we're going to find the information first. Sorry, you got the x-intercepts and you got the graph, whatever. You were able to draw and you were able to use the algebra to confirm. Yes, you use that equation, you use the x-intercepts, and you use the graph to draw the graph. You were able to confirm. Here, we're doing the opposite. We are essentially doing the algebra first to make sure that we can confirm using a graph. Does that even make any sense? What am I saying right now?
Yeah.
Okay. Let me show you. Starting off, please look at this and tell me what the domain ought to be. If you need to, turn it into a x plus 1 linear equation to talk about what the domain ought to be and then flip it. Or take a look at the denominator using your grade 11 skills. Give me the domain with the restriction. Okay? It's up to you. So part A, I like to spell out the samic, the D saying x can belong to anything, but x can't equal -1. Good. Done. Done. Let's move on to I. Let's do the easy one. The y-intercept is when x equals 0. So what is f at 0? 1 over 0 plus 1 equals 1. Therefore, my y-intercept is 0, 1. What about the x-intercept? The x-intercept is when y equals 0, which means f of x is equal to 0. What is the x value when the y value equals a 0? Right? There's not vertical. Yeah, this thing can't equal a 0. Take a look at the denominator. It's never going to equal a 0. So you'll never have a fraction of x over 100 or whatever the case may be. Therefore, no x-intercept, which should tell you what the horizontal asymptote is, okay? So there. Here, just think about it. So we don't have a y value. Y can't equal a 0. That's basically what I'm saying. Y can't equal a 0. So let's move on. This same S, symmetry. I don't need to talk about that now. In fact, you could calculate symmetry to help you. Symmetry to help confirm your sketch. Do later if you must. And you know how to calculate symmetry, right? You can check if this is equal to that, or you can check if this is equal to that. Sorry. Wait a minute. No, this is a vertical. I need a horizontal. So this is if it's even, sorry, and this is if it's odd. That's why I had issues. That's why it was looking funny. My habit plus a mistake. There it is. Okay, so you don't have to do that now. It's a lot of work sometimes. So it could be a waste of your time if you're able to do all the other ones properly. Dysamic, A, asymptotes. So this requires a little bit of thinking. What's the vertical asymptote? Based on what you've seen here. When did I get a vertical asymptote? What does the vertical asymptote correspond with? The x-intercept before. Vertical asymptote. Remember that x cannot equal -1. Therefore, the vertical asymptote is at x equals -1. About the horizontal asymptote. You should have found out. So again, vertical asymptote, you can take a look at your domain and that should correspond right there. Horizontal, yep. Yep. Y is equal, cannot equal to 0. Therefore, HA is at y equals 0. And there's one more thing that we haven't learned and we're not going to talk about right now. It's called oblique asymptote. And you're going to get that in chapter 3.3/3.6, okay? So don't worry about that. This I. Lastly, intervals. I'm going to do the chart, the interval method. And here, you've seen it already. All x-intercepts and vertical asymptotes, remember? What are the x-intercepts? There is no x-intercept. What are the vertical asymptotes? There is one vertical asymptote. And what is f of x? The only part of f of x that will change the sign is the denominator portion. So this is VA, so you can't touch that. So a number under -1, let's choose -100. 1 over -100 plus, that's going to be a negative. So my function is going to be negative here. How about this side? So a number bigger than -1. Why not 0? 1 over 1 is a positive. So my function is going to be a positive. To the left of my vertical asymptote, I will have a negative side of the curve. To the right of my vertical asymptote, I will have the positive side of my curve. Using these 5 chunks of information, I am going to sketch the graph. Here we go. So this is why you do these 5 steps. Ready? I have a y-intercept at 0, 1. I have a vertical asymptote at -1. And that's going to be dotted. Okay? I will also have a horizontal asymptote at y equals 0. There. Let me label that. Okay. What else do I know? So I've got my y-intercept, I've got my vertical asymptote, I've got my horizontal asymptote. All I have left is the chart. Where is the graph? Can you visualize the graph already without the chart? Based on this? Maybe. What does the graph tell you? If I am to the right of my vertical asymptote, I should be above the y-axis. Oh, sorry, x-axis. And because I have to be here, I have to stay above this dotted line, and I need to stay to the right of this dotted line here. It's going to look something like And what about the left? If I am to the left of my vertical asymptote, I need to be negative. I need to be under the x-axis. It's gonna look something like this. Or how about I draw it like instead, going from left to right. Some teachers will ask you to plot a accuracy point. Like for example, you say, oh, I don't know where this line is supposed to go, so give me at least 1 or 2 dots by plugging in an x value under -1. So let's say I plugged in f at -2. That is 1 over -2 plus 1. That is equal to -1 over 1. So at 2, my dot should be here. So my curve should be a little bit better. I will not worry too much about that. If I ask you for an accuracy point, sure, go for it. But by default, I'm not going to worry about that. I am looking for your general shape for now. Okay. So we're running a little bit short on time. I am going to quickly do the second example. And the third one, I'll get us started, but I want you to finish it after we get the details down. Okay. Quickly. Would you like to try it or do one more time? One more time? Okay. Domain. X belongs to real numbers as always, but I can't have 2x minus 3 equaling a 0. So I'm going to check. If that equals a 0, that means 2x equals a 3. That means x equals 3 over 2. Well, that means using this as my calculation, my restriction is x cannot be 3 over 2. Done. Intercepts. Let's do the easy one first. Y-intercept means x equals 0. What is f at 0? 1 over 0 minus 3, which is 1 over -3. So I have an x-intercept of 0, -1 over 3. What about the x-intercept? In other words, f of x is equal to 0. Y equals 0, right? Is that possible? No. Good, thank you. The numerator is a 1, which means y cannot be a 0. So you might want to be careful, keep that in the back burner because that's going to be your asymptote. Okay? So no x-intercepts. Moving on. Dysamic. S. Do later. Do if needed. I. This A. Asymptotes. Is there a vertical asymptote? Yes. Is there a horizontal asymptote? Yes. Is there an oblique? Well, we didn't learn it. Did not learn. You have to wait and be patient. You probably don't want to learn it anyways because a lot of students don't like it. Intervals. Let's do it. And I need that as a solid line. So, okay. X-intercepts, none. Vertical asymptote, 3 over 2. Parts of the graph that will be negative, or that could be a negative, that is 2x minus 3, which means f of x. Okay, here we go. Smaller than 3 over 2, let's try a 0. 0 minus 3, that's a negative, so my function is a negative. The function cannot touch this dotted line, so I'm going to write VA to remind myself. And then a number bigger than 1.5, that's, let's say, like 10. It's going to be a positive, so my function is positive. Okay, let's do it. X-intercept, none. Y-intercept, negative 0.1, negative 1 over 3. Vertical asymptote, 1.5. Horizontal asymptote, 0. I will label it. And let's see if my chart agrees. My chart says, if I'm to the left of the vertical asymptote, I gotta be in the negative. If I'm to the right of my vertical asymptote, I've gotta be positive. In your head, I'm hoping that you already see a shaded area. If I'm to the left of my vertical asymptote, I've got to be here. And if I'm to the right of my vertical asymptote, I've got to be here. How do we reconcile that? You could do some accuracy points here, but your graph should look something like, and like that. And if you're curious, you can try on Desmos and you'll see the exact same thing. How about I do that for you very quickly? Y is equal to 1 over 2x minus 3. There it is. Right? 1.5, 3 over 2, vertical asymptote. Y equals 0, the horizontal asymptote. I have my y-intercept, negative 1 over 3. Everything matches based on what we've analyzed. Yes?
I just wanted to ask, so you know the horizontal asymptote is 0 because there's no x-intercept?
Correct. There's nothing touches that x-axis. I have 10 minutes with you. I'm going to start dysamic, but you draw. Specifically, I just want to get to the asymptotes because it's a little funky. Okay? And then I want you to try drawing it afterwards. And then tomorrow, I wish I had some more time. Okay. Domain. X belongs to any real number, but you can't have 5 minus x equal to 0. That means negative x cannot equal a negative 5. So x cannot equal a 5. A better way of dealing with this, if you want, is changing it so that it's more familiar to you. You can always do this, which is the same as, I think it's a lot better for your brain if you see the x term as a positive. It's a lot easier to work with. And so, take a look, x can't equal a positive 5. Does that make sense? Sets. Let's do y-intercept. When f is a 0, that's 4 over negative 1, 0 minus a 5, which is 4 over 5. Oh, well, I don't know if that's a good or a bad y-intercept, but there it is. This is my x. Oh, this is my y-intercept. That's for x-intercept. Will f of x ever equal a 0? No. Never equal a 0. Okay. So So no x-intercepts. Here we go. All right. So here's a new one. So skip symmetry. So later, this amic, asymptotes, vertical asymptote. Be careful. What's my asymptote here? Yes. Be careful, all right? And would you please leave some space here? Horizontal asymptote, what is it? Zero. Good. And then leave some space here. We'll do the chart up here, or we'll do the chart next to it, asymptote interval, and then we'll draw it up here, okay? The reason I'm asking you to leave this thing is because when we look at it, revisit this tomorrow, I'm going to show you how you can confirm this drawing by testing a limit. Ever heard that before? Grade 9? No? Testing a limit. So for now, let's get to drawing. You don't have much time today, unfortunately. What is my VA? No x-intercept, and okay, so that's just the 5. And what part of this function could change sign? The -1 will always be -1. The x minus 5 can change signs. Here we go. This is a vertical asymptote. You can't touch it. Number under 5. Well, we'll do 0. The -1 is always negative, but 0 minus 5 is a negative. That's going to be in the positive side. A number bigger than 5. Let's try 10. -1 will always be negative. 10 minus 5 will be a positive. This function will be a negative. So if I were to draw all right, where is my, okay, vertical asymptote is at 5. Let's do 5. Let's say that is dotted. Y-intercept is 4/5. There is no x-intercept, which also implies we have a horizontal asymptote. Okay, and then based on this, any point to the left of my vertical asymptote has to be a positive. So left of my vertical asymptote has to be a positive. Any value to the right of my asymptote has to be a negative. So I'm going to assume keyword, that it's going to do this, and it's going to do this. It's just a repeat of learning how to sketch. Now you might be asking, Mr. Kim, how do you know that it's going to behave like this so close to the horizontal asymptote? How do you know that it's going to behave so close to the vertical asymptote? Well, I'm going to try to show you that by doing something called testing a limit. So getting infinitely close to these dotted lines tomorrow. Okay? So it might be a very intense lesson tomorrow just before the long weekend, but I hope you'll hang on. For homework, I highly recommend you practice the dysamic steps through the textbook. You don't have to do all of them if you don't want to. You could save a little bit later because the lesson is not complete. I need to test the limit with you, but do as much as you can. Okay, we still have a couple of minutes. You can slowly pack up, and I will stop the video here.